Uh, my name is Anil Narasimha. I'm the CEO and co-founder of Mekonos. First off, thanks to ARM for giving us the opportunity to showcase a little bit about what we do in Mekonos. We're San Francisco based, so our headquarters are in the Bay Area. And what our goal really is to create a universal delivery platform of any kind of cargo into any kind of cell ex vivo. And the way we're doing that is by utilizing controllable nanoneedles on a silicon chip. So I like to do this kind of a thought exercise of, what if you could transfect any fragile cell? So we're talking, primary cells, immune cells, stem cell niches, with high viability and high efficiency. So obviously that's a standard that everyone utilizes. Large multiplexed payloads at single cell level precision, and then a control that doesn't really exist right now in the delivery space. And so at Mekonos, what we're excited to kind of really showcase is having preclinical data demonstrating delivery into various fragile cell types, and I'll show you guys some data in just a little bit, with at least 95% viability and at least 70% efficiency of delivery of any type of cargo and any type of payload, or any type of cell, loading multiple cargoes that sometimes even exceed 100 kb, whether that's a plasmid or a linear piece of DNA, onto nanoneedles that are positioned where you're delivering a single needle into a single cell, with finely tuned dose control, meaning can you control the amount of payload that goes into a single cell, and then targeted delivery. Let's say you want to do nuclear delivery to bypass the cytoplasm, especially for DNA payloads. So what we're really trying to do is, how do you build a future of cell therapies on a chip? What we're really trying to do is create a level of automation and precision at scale that doesn't really exist in the delivery space. And so really creating a proprietary cell engineering platform, ex vivo obviously, taking advantage of scalable silicon technology for hyper precise, and when I say hyper precise, I mean single cell level delivery of any type of molecule or molecules into any type of cell. And so how does this work? And I'll show a video in a couple of slides that I think is a better representation of how our technology works. But you can think of our technology as really kind of three components coming together and working synergistically. The first component is a nano-engineered silicon needle array chip. So we have a chip that we've developed that has an array of nanoneedles that are controllable, that are positioned to mechanoeffect, as we've trademarked this recently, different payloads into single cells. The second component is a cell trapping chip that utilizes microfluidic technology that we've developed. And the goal here is to really collect cells at a single cell level into specific nodes. And then so you pair the needle chip with the cell trapping chip, so you get single cell level mechanoeffection of your payload of interest, but just massively parallelized. So picture something like IVF or atomic force microscopy. We've shrunk that down and scaled it out. And then the third component is a proprietary surface chemistry that we've developed and patented that basically facilitates attraction of a payload to the surface of the needle, and then the release of the payload once the needle is inside the cell. So so these are solid needles, so they're not hollow for a variety of reasons. And so because they're solid, we had to develop a chemistry on the surface of the needle to basically facilitate attraction when the needle is outside of the cell, and then release once the needle is inside the cell. And so we're fortunate to have some really good scientific advisors to really develop that technology. So how does what does our workflow look like? So as you have your cell population, however you want to isolate those cells, through PBMCs or whatever cell type that is of interest for you. You flow your cells into our system. They get trapped. Then we have a needle chip via optics that kind of aligns itself with the trap cells. Then you do your poking, you do your mechanofection, and then you collect the cells on the back end. And so you can either put those back into culture or immediately analyze them. And then this whole process takes minutes. And so, as I was alluding to earlier, let me show you. Oh, actually, sorry. One more slide. So we have a product which is really exciting. We were able to get our first kind of product in late last year that we're codenaming ARC, and it's an RUO platform at this point. Obviously, our goal moving forward is to get into GMP, but there's the chips that are consumables and a bunch of other kind of strategies that kind of come together and are aligned to kind of really make this platform work. So with that, let's kind of go with the video if that's possible to play. Or is it maybe? Oh, here we go.
Some innovations are small steps. Others, like the technology being developed at Mekonos, open up a world of new possibilities.
This is a cargo that I'll be loading onto our fluidic cartridge.
Now we'll prime the chips before loading cells and cargo.
Our mechanofection platform integrates pick-and-place robotics, silicon chips, surface chemistry, precision optics for automation, and a custom microfluidics cartridge. As the pick-and-place holder brings down the nanoneedle chip, the needles are already functionalized and ready to receive cargo. Our aptamer-based surface chemistry can be used to bind multiplex cargo, in this case, a Cas9 RNP and a DNA donor. Below the nanoneedle chip is a cell trapping chip containing an array of pores. After entering the cartridge, the input cells travel through a fluidic channel towards a closed flow cell. Upon arrival, they are captured above the pores of the cell trapping chip. These individual sites are precisely aligned with the nanoneedle chip, so there is one needle per cell. The nanoneedles are gently lowered to their respective cells. The depth of travel is finely controlled, enabling nuclear delivery of the cargo. The modified cells flow off the chip, traveling along another fluidic channel to an output reservoir, ready to be collected. By combining the power of semiconductor technology, microfluidics, and surface chemistry, Mekonos is building the future of cell therapies on a chip. Let's kickstart a new era of cell therapy together.
All right, thank you. Hopefully that gives you a better idea, or at least visual, of how our technology really works. Our next goal in our product development, so as you saw, the ARC is an RUO platform, but we're in the process of creating a GMP level platform that not only still kind of brings the basics of our technology in terms of nanoneedle delivery and needle-based delivery, but it's more scalable and because we have the ability to parallelize chips. And so this is kind of our vision for a scalable manufacturing platform, which is our goal as a company moving forward. So what are our unique capabilities? I was mentioning a couple of these before. The critical thing for any delivery platform, regardless of whether it's us or any electroporation or viral vector strategy, is you have to have viability, like high viability. You have to be gentle on immune cells and stem cells, especially in the cell therapy CGT world. Dose control, right? So because we have a surface chemistry, we can tweak our surface chemistry to basically create different stoichiometric ratios of cells, of cargo, different types of cargoes going into a single cell. Nuclear delivery, sequential delivery. So we're only creating one pore on the membrane as opposed to maybe an electroporation strategy that creates multiple pores. And so even in our hands, what we see is the recovery time is really quick for these cells to recover from the manipulation event. And so we're talking, minutes, let's say an hour, if you want to engineer the cell for whatever application that you're intended to do. Large cargoes that I'll show you some data in just a second, multiplexing cargo, and then I think at the end of the day, what we're really trying to create is a single cell level platform, right? And so, especially in the CGT space where, these cells are being, transfused back into the body, being able to kind of really address every single cell, I think is a critical next step to kind of really ensure that precision, to ensure that you want the cells to behave the way you want them to behave. And so this idea of, what is this single cell level delivery? What does this what do we bring to the table, right? So I've mentioned some of these already, but intraneedle multiplexing, we can do iPSC editing with really high efficiency and high viability, sequential editing that I was just talking about, large payloads, nuclear delivery. And then at the end of the day, because this is a silicon platform, we have the ability to generate single cell level data, which allows us to create better CMC packages in the future. I might have skipped. Okay, so large plasmid. So this is a 15 kb plasmid that we compared with lipofectamine in this case in hematopoietic stem cells. So we have a number of data sets. I'm just going to show you some representative data. And typically we get that 70% efficiency with really high viability. In T cells, these are knockouts of primary CD8 positive T cells. With using Cas9 RNP, and again, that knockout compared to nucleofection, we're getting some kind of better on both on the efficiency and the viability fronts. Macrophages are notoriously really hard to manipulate, especially for DNA, because they're really refractory to foreign DNA. And so with our technology, again, addressing every single cell, we have the ability to generate some really positive data for engineering of macrophages. Multiplexing, so in this case, we've multiplexed 3 different payloads, and then if you look at the cells that were manipulated, almost, a great percentage actually has all 3 payloads. So this ability to multiplex multiple payloads is huge, right? Because we're talking, especially for a gene editing application where you got to deliver the guide RNA or the DNA donor as a knock-in, or even the Cas9 or whatever Cas that you're using. We have the ability to do that all separately or all in one bulky vector if that's what's required. So we're very flexible in that regard. And then large plasmids. So we announced a collaboration last year with a synthetic bio company called Neochromosome. And one of their requirements is a 114 kb plasmid. And so this is unoptimized, but we actually have the ability to deliver a 114 kb plasmid, which is 10x what a lentiviral vector can do. I was mentioning dose control. So in this particular data set, what we did was we kept everything constant, and then we changed a particular aspect of the experiment, whether it was the input concentration of the payload, whether it was the residence time of the needle in the cell, or whether it was the depth of penetration that the needle goes into the cell. So all of that is controllable in our hands, right? And what you see is this kind of linear progression, which kind of equates to that, however you want to change or whatever experimental conditions you want to do, you have the ability to deliver more of the payload into a single cell or less of the payload, kind of depending on how you tweak your experimental conditions. And so that's really exciting. I don't think anyone else can do that in the sense that can you deliver different ratios of payloads going into a single cell. And so for applications like iPSC reprogramming and other things, this becomes really, really useful. We, I'm at time right now, but we have a number of partnerships that are ongoing right now at the preclinical stage. We're always looking for more, and so my head of BD, Jake Lesnick, is here as well, probably having some partnering conversations. We're fortunate to have an awesome scientific advisory board, including Irv and Carolyn, who are serial entrepreneurs, and Cassian Yee is a Parker Fellow at MD Anderson. Our leadership team has a lot of experience in a variety of fronts, as I was mentioning Jake, who's here at the conference as well. So with that, thank you for taking the time to listen to kind of what we're doing at Mekonos.